How's it going, Brian with a Y here? And I just came across a crazy discovery on the internet just by Googling. I got done with my work today and I was just kind of messing around on Google and I wanted to do a search on the history of orthotics and prosthetics to kind of understand the progression from leather and almost blacksmiths and tradesmen that would sculpt these devices, and then moving into like the wartime era and how prosthetics and orthotics changed then. And I came across this article that was only from 10 years ago, so a decade ago in 2011, from these two researchers who were interested in discovering a workflow using something like 3D scanning, computer aided design, and 3D printing slash additive manufacturing. And it just popped up and I started to read over it and I was like, this is crazy. This is crazy. Okay. I got to be honest, I am in the digital workflow. That's what I do for a career. So it just excites me. I'm passionate about it. I'm passionate about how we can use steps in digital tools to ultimately improve the devices that are being made for patients, which help in gait and which are more comfortable. And there's a multitude of reasons why you would use digital tools to produce orthoses and prostheses. But when I came across this from 2011, it blew my mind. I didn't know that there was research being done into this. I didn't know that there was research being done 10 years ago, and it's revealing. So I just want to read the abstract right quick and then kind of go through some of the areas within this report that stood out to me and are a part of my daily workflow now, 10 years later. I am working daily to introduce a digital workflow to clinicians all over the country. And sometimes I get that look like I'm bringing something brand new to the table, and I'm like, wait, let's pump the brakes here. I'm going to start sending this article and be like, look, 10 years ago we were looking at this. Let me tell you what we've done in the last 10 years to improve it. And it's evident here is if this is the baseline of where we started, and we've only improved from there. Some of the more highlights that I'm seeing is that we've got more materials and the cost of manufacturing has came significantly down. That I will show you in a minute, but golly, the pricing of these AFOs that they were printing were in the thousands of dollars, whereas today they're sub $500 and oftentimes even lower than that for a better printing process and better materials. So cost has came down. There's been advances in software and scanning. Their scanning techniques were pretty manual. I mean, they printed out a 2D piece of paper and placed targets. They printed out the targets and then taped those targets on that paper to their patient's leg and then captured the images there. Excuse me. And then transferred that imaging to their software program and had templates already created. And the designs were already created based on where the landmarks were. We're talking about today how we can use templates to really optimize the design process of these orthoses and prostheses that we're creating daily. But the truth is that template design is at the very core, according to this. If this is the beginning of research in 2011, it's at the very core of where the industry started in regards to additive and 3D and O&P. I want you to share with me any research that you have that is predated 2011, because this is like candy. So the abstract. Passive dynamic ankle foot orthoses constitute a class of ankle braces that rely on material properties and physical features to establish functional characteristics such as bending and rotational stiffness. We have developed a novel framework that combines a fully parameterized PDAFO computer aided design model and freeform fabrication to rapidly manufacture customized PDAFOs. The three-dimensional locations of select anatomic landmarks serve to customize customize the PDAFO CAD model. A virtual orthopedic alignment process and selection of discrete design parameter values further customize the orthosis, which is fabricated via selective laser sintering. CAD models were customized and full-scale orthoses were manufactured for two non-disabled subjects. The surface of one half-scale CAD model was marked with 3 mm hemispherical dimples, and 4 orthoses were manufactured in different build orientations and positions. Dimensional accuracy was determined by calculating discrepancies between corresponding CAD and fabricated orthoses interdimple distances. Subjective evaluations of the full-scale PDAFOs following in gait were positive. Dimension discrepancies were well under a 2 mm tolerance, 2 millimeters, for the 4 half-scale orthoses. Mean foot plate, strut, and cuff component discrepancies were plus or minus 0.31, 0.28, 0.34, 0.08, 0.52, and 0.39 millimeters, respectively, and 0.29 plus or minus 0.23 millimeters as well for the overall orthoses. That's pretty good dimensional accuracy. Dimensional accuracy of the rapid customization and manufacturing framework was well within tolerances suggested in the literature. Okay, so what does that say? That says, number one, this is what really sticks out to me, is that they have created, where is it? We have developed a novel framework that combines a fully parameterized computer-aided design model and free-form fabrication to rapidly manufacture customized PDAFOs. So they are claiming that they have created a digital workflow in 2011. Very nice. What also? That the dimensional accuracy of the rapid customization and manufacturing framework was well within tolerances suggested in the literature. I face this today as well, as people say, well, what about the tolerances of even the scanning? 10 years ago, we were well within those tolerances. So I would say that today we've only improved. Okay, so what is another thing that sticks out here right here in the beginning? In 2007, the prescription of orthotics accounted for $458 million of Medicare expenditures alone. Therefore, the capability to rapidly design, manufacture, customize orthoses with precisely controlled characteristics would help transform the PDAFO customization and fabrication from a craft-based industry into a modern clinical specialty. Yes, they're right. I'm saying that today as well. The modern clinician uses digital tools to create better fitting, well-made, time-saving devices that improves the outcomes for their patients. I don't know how many times I've said that, but they were saying it 10 years ago as well. Let's see, they're going through the traditional workflow, and then they're going through how I don't read this fast, but I'm just kind of like skimming at, obviously. They're going through how the SLS process works. Love that. Trying to explain that to the clinician is difficult because it is a very technical process. An advantage of the SLS process is that cost of manufacturing is primarily a function of part volume and not part intricacy. Thus, this method is ideal for fabricating objects with unique, complex geometry. Louder for the people in the back. Yes, this form, powder bed fusion, this form of additive manufacturing allows, it actually gives you increased complexity without increased cost. So you could create your literal imagination and not see the increase in cost that you would expect if you were going to be traditionally manufacturing something like this AFO. Because of its intricate details and layers and things of this nature, this would be very difficult to CNC manufacture, especially, I mean, just all the different areas here. It would be quite expensive just because there's so many different setups. 3D printing and additive manufacturing allows your imagination to really run wild. Excuse me, what else stood out? They're using Inventor Professional version 11 from Autodesk to do their design. I don't know what version Inventor's on now, but Inventor is still around, which is really interesting. This one was too. The strut component is sized as a function of the shank length and shaped by a series of 11 parallel 2D profiles that are offset in the posterior direction from the shank segment longitudinal, I'm sorry, I don't want to try to say that again, by an operator specified distance. The 11 profiles are lofted together to form a 3D strut component. The top and bottom strut segments are beveled to enable attachment of the upper and lower spans. Imagine you're shanking. I mean, you do that now in design. Lofting, not shanking. Lofting. This is a 2D piece of paper. That's 2D. And they had these targets on there. And they would tape this piece of paper to the patient's leg and then take their scanner, which was a Faro arm scanner, and capture this image. And then come here where they had template-based design, and they would select these landmarks in the digital space, and then the splines would connect and they would loft, and you had the shape. We're doing that today as well. This is, it just blows my mind. It blows my mind. There was one section here that talks about costs. Cost analysis for rapid prototyping technologies must also be considered and are sensitive to numerous factors. Freeman and I don't want to try to say that, reported an hour-based cost range of US $1,560 to $3,480, $60 an hour, which included preparation, material, and build time to fabricate a prosthetic test socket using stereolithography. New virgin Duraform EX natural plastic material cost approximately US $4 per cubic inch. In this report, the PDAFO customized for the female subject required a 37-inch cubed of material at a cost of $148 for materials alone. Approximately 1 hour was needed for obtaining digitized landmark data and customizing the fully parameterized PDAFO CAD model. An additional hour of technician time was required for executing the SLS manufacturing process. which can require approximately 24 hours of machine time to complete. Once built, the PDAFO requires strap added to the cuff and padding inserted on the interior surface of the cuff and superior surface of the foot plate. Approximately 30 minutes of effort in total, 2.5 person hours were required. This is substantially less than the traditional PDAFO manufacturing methods and delivery times. While this project was not subject to business-related costs associated with build time, machine depreciation, material waste, and annual maintenance cost, a quote of $3,327.84 obtained from a commercial SLS manufacturing site to manufacture one full-scale PDAFO indicated that a substantial level of overhead may accompany current commercial manufacturing models. As a comparison, one patient reported a 2007 cost for manually fabricated PDAFO of $8,000 per orthosis. What? Number one, they were charging $8,000 per orthosis in 2007. Whoa. No way. Number two, the print time for one of these in SLS in 2007 or around that time was $3,327. Holy cow. Holy cow. The cost of a build on multi-jet fusion is anywhere from $300 to $1,200. How many of these can you fit in a 15-inch by 12-inch by 15-inch build space? You're talking 1, 2. I mean, you could put them all in there whichever way. It's an isotropic build space. And you could fit how many of these in there? All around, this was a report that blew my mind. I recommend that you check it out wherever you are. The link will be in the comments. If any of this stood out to you, of course, I was reading really quickly, but this was just what stood out to me. I ask that you put it in the comments. Let's chat about it because I love it. I love it. Wherever we are in 10 years from now, I hope that I one day am able to contribute to a research project that someone like me can reflect back on and say, holy cow. Because this was quite amazing. I enjoyed that. Wherever you are in the world, have a great day. Brian with a Y.